Hey everyone, and welcome to this explainer. So take a second and just look around the room you're in right now. You probably see a very physical space filled with solid, physical things, right? Chairs, a desk, the screen you're watching this on. But what if I told you that the universe is not actually made of solid stuff like wheels and gears? What if it's actually made of invisible, continuous, mathematical functions? Well, today, we're going to fundamentally shift how you view reality. We're going to demystify electromagnetism and take a deep dive into the completely abstract world of fields.
Now check out this slightly cheeky quote on the screen. It says, "And God said," followed by four very intense-looking mathematical equations, "and there was light." These are the famous Maxwell's equations. And this isn't just some funny science meme. These math symbols literally describe the creation and behavior of light itself. Every single thing we can see in the universe is governed by these exact symbols. It's kind of mind-blowing.
The brilliant physicist Freeman Dyson really hit the nail on the head with this paradigm shift. He said, "To see the beauty of the Maxwell theory, it is necessary to move away from mechanical models and into the abstract world of fields." So the absolute crucial takeaway here is that to truly understand our reality, we've got to stop looking for physical, mechanical parts. No tiny microscopic billiard balls bouncing off of each other. We have to start looking at geometry and mathematics.
And the guy who practically forced us to make that massive mental shift was James Clerk Maxwell. Back in 1865, Maxwell published this groundbreaking paper called A Dynamical Theory of the Electromagnetic Field. Honestly, it's arguably one of the most significant moments in the entire history of the physical sciences. He just completely revolutionized how we understand the forces of nature by giving us this beautiful mathematical framework for how electromagnetic fields evolve. But here is a totally wild historical fact for you. His genius? It was largely ignored by the scientific community for 20 long years. Why? Well, mostly because his original work didn't look anything like those four elegant equations we just saw. Nope, it was made up of 20 overwhelmingly complex equations. Most physicists at the time literally just didn't have the algebraic tools to grasp them, and mathematicians really didn't like his physical language. Plus, pretty much everyone was still stubbornly trying to explain the universe using those old mechanical wheels and gears.
All right, Section 1, Rethinking Reality. What are fields? Let's get into it.
So, if the universe isn't some giant mechanical clock running on hidden gears, what exactly is a field? Well, simply put, a field is just a mathematical function acting throughout space and time, possessing zero material or mechanical substance. I know, we desperately want to imagine a substance, right? Like a physical fluid flowing through the air. But in reality, there's absolutely no physical stuff there. There's no everyday intuition we can rely on for this. The mathematics are the interface. It is quite literally just numbers mapped across space that change as time ticks by.
Let's try to ground this with something a bit more familiar, okay? A scalar field. A scalar field assigns just a single numeric value to every point in space. Think about climbing a mountain. You know that for every kilometer you hike up, the temperature drops by a few degrees. If we map the exact temperature at every single point on that entire mountain, boom, we've created a scalar field. Notice how right at that specific coordinate on the grid, the temperature is precisely 27.6 degrees. No arrows pushing anything, just a single number locked to a specific point.
And this graph brilliantly illustrates what happens when we add the element of time into the math. We're looking at a partial differential equation here, specifically the heat equation. It's not just showing us the temperature frozen at one static spot. It's mathematically modeling how that temperature changes. It shows how heat physically flows and smooths out across that surface as time moves forward. It is, quite simply, a field evolving.
Moving right along, Section 2, Vector Fields, Visualizing the Math. Now let's graduate from simple numbers to the forces we actually feel every single day. Unlike a scalar field, a vector field assigns both a magnitude and a direction to every point in space. On one side here, you can imagine a fluid flowing, where every little arrow tells a water molecule exactly how fast to go and in what direction. On the other side, we see the exact same mathematical concept applied to planetary gravity. The arrows all point toward the masses, perfectly showing both the direction and the strength of the gravitational pull.
To really grasp Maxwell's equations, we honestly just need to wrap our heads around two pretty intuitive ideas about how these vector fields behave: divergence and curl. Divergence acts kind of like sources and sinks. It measures whether our imaginary field fluid is converging into a point or diverging out of it. Curl, on the other hand, is all about rotation. It answers the question, how much is the field spinning?
Let's look a little closer at positive divergence first. Imagine drawing a tiny circle right around that center point.
If more arrows are pointing out of the circle than are going in, you've got yourself a source. The fluid is expanding outward. Mathematically, the divergence here is calculated as a positive 1.0. Now, if the arrows were all pointing inward instead, it would be a sink, and that number would flip to a negative.
What makes this math so incredibly powerful is that even in a highly chaotic, swirling flow, we can pinpoint exact coordinates. Look right inside that localized, boxed-off region. The math calculates a positive divergence of 0.65. So we instantly know for sure that that specific tiny point in space is acting as a source.
Okay, so what about curl? Honestly, the absolute best way to picture this is what I like to call the imaginary paddle wheel test. Imagine taking a tiny microscopic paddle wheel and dropping it directly into our vector field. Which way do the arrows make it spin? If the field pushes it into a counterclockwise rotation, the math gives us a positive curl. If it spins clockwise, it's a negative curl. It is quite literally a measurement of rotation within the field.
Section 3. Unifying Forces. Electricity and magnetism.
So how do divergence and curl actually describe our universe? Well, this is where Maxwell's genius truly shines. The first two of his equations rely entirely on divergence. First up, we have Gauss's law, which basically states that electric flux, the flow of an electric field, is proportional to the charge it surrounds. Electric charges can exist all by themselves. A positive charge acts as a source, a negative charge acts as a sink. But Gauss's law for magnetism is incredibly fascinating. It proves the magnetic flux through a closed surface is always zero, meaning you can never ever have just a north pole or just a south pole. Magnetic monopoles simply do not exist. What flows out must absolutely flow back in.
The second half of Maxwell's equations relies on our other friend, curl. The Ampere-Maxwell law shows us that electric currents literally generate curling magnetic fields. So, if you run electricity through a wire, a magnetic field naturally wraps right around it. And Faraday's law gives us this beautiful, perfect symmetry. A changing magnetic field produces a curling electric current. Electricity creates magnetism, and magnetism creates electricity. They are entirely intertwined.
And this leads to the ultimate mic drop revelation. By combining these equations, Maxwell discovered that these changing electric and magnetic fields propagate through space as a wave. And when he calculated the speed of this wave, the math spit out a very specific number. It was the exact speed of light. Maxwell proved, purely through mathematics, that visible light is nothing more than an electromagnetic wave dancing through these invisible fields. No way, right?
Finally, Section 4. Modern power. Powering our world.
So why does all this abstract math matter to us outside the physics lab? Well, because these mathematical functions are the literal foundation of your smartphone, your computer, and your car. Electrical engineers are basically just manipulating Maxwell's equations all day long. They use a resistor to impede the flow of current. They use a capacitor, which physically stores potential energy entirely inside an electric field. And they use an inductor, which is just a coil of wire that stores energy inside a magnetic field. Our entire electrical grid, everything that powers our modern world, is just a masterful manipulation of divergence and curl.
And if that wasn't enough, here is a totally mind-bending fact to add to the mix. Fast forward a few decades after Maxwell, and Albert Einstein enters the chat with special relativity. He proved that if an observer is moving at the exact same speed as the electrons in a wire, the magnetic force disappears entirely for them, and they only feel an electric force. Thanks to Einstein, we now know that magnetism is merely a relativistic side effect of moving electricity. They aren't just related, depending entirely on your point of view, they are exactly the same thing.
Which brings us to the final thought I want to leave you with today. Look around your room one more time. The table, the walls, even your own hands. At an atomic level, literally none of this is made of solid objects touching one another. The repulsive force you feel when you clap your hands together, that's just the interaction of electromagnetic fields. So I've got to ask you, are you really interacting with a physical, solid universe? Or are you just swimming through a continuous, invisible mathematical field? Something to think about, right? Thanks so much for learning with me today, and I'll catch you on the next explainer.